Hey guys, so today I'm going to be sharing with you how I made a real-time object detector software for self-driving cars. So at the time of filming this video, I'm 17. There are two things a 17-year-old can do. They can code and they can drive.
Spoiler alert, I'm not very good at driving.
So let me tell you a quick story. I was driving down along Bloor, about to make a turn towards Bathurst. On a normal turn like this, I checked for any oncoming traffic, bikes, and people walking towards my car. However, I didn't notice anyone on my blind spot, but luckily nothing bad happened after my dad told me that someone was there. But in a simple situation like this, I found it very difficult and kind of stressful to make a simple turn. So when I realized that computers can detect objects and people around its environment, my mind was just blown apart. Like, how do they do this? And so the answer to that is using computer vision. So if you don't know what computer vision is pretty much allowing computers to gain a higher level understanding of its environment through images or video feed. So over time, if you give a busy street like this, the computer will be able to recognize that there are cars, people, and traffic lights in that image. So there are many different ways to approach computer vision problems like this. One of them is using Mask Residual Convolutional Neural Network. Yeah, that's a big name, so let's call it Mask RCNNs. This network is designed for instant level segmentation. What do I mean by that? Compared to semantic level segmentation, instant level segmentation classifies common groups of pixels into different labels. So if we take a dining room, for example, there are many chairs around a table. In instant level segmentation, the network will be able to recognize each of these chairs individually, whereas in semantic level, they'll classify all these chairs as one class. And this is very similar to another network called faster RCNNs, which is another model that detects objects, which is what Mask RCNN is actually based off of, but with the additional component of being able to add segmentation masks for every object. So if you don't know what faster RCNN is, here's a quick rundown. So faster RCNN detects objects as well and also places a box around them. So going back to our chair example, over time when we train the model in faster RCNN, it'll learn that it's a chair, it'll output that and be like, hey, that's a chair, let's tell the user that and let's put a box around it too. Now in Mask RCNNs, for every chair that we just detect, we'll also shade it in with a color. And this helps the computer understand the object's spatial layout more in detail. So what's the big deal with all these masks? Well, one, it's a simple and flexible framework. Two, it's multi-purpose, so it can detect objects in different positions without having to retrain it. And three, it improves the overall accuracy and performance compared to all other single model entries on competitions. Now that we understand the higher level concept of Mask RCNNs, let's dive more into the architecture. Because Mask RCNNs are based off of faster RCNNs, the architecture for that consists of a backbone and the head. The backbone, which comes before the head, uses residual neural networks to extract features of specific images. So whether that's detecting edges and later learning that those edges are cars, this gets passed to the head, which learns from that and performs bounding box recognition. So like going back to your example, like, hey, spotting that that's a chair and placing a box around that chair. So where does the mask part come into play? We first have to understand that the mask branch is independent from the classification and bounding box branches. So let's say we have 25 different classes. The mask branch will learn how to predict 25 masks as individual inputs instead of a single input with 25 different channels. And this avoids competition for generating masks between classes and improves the overall accuracy. So you might be wondering, how does the computer get so good at putting on these masks? And just like humans, we learn from our mistakes, and we can represent this through a loss function for the computer. So in the case of classifying masks, you either get the mask placed correctly or incorrectly. And this will be a binary cross entropy loss function in this case. So what do these words mean? Binary, which means two, so either you're right or wrong. Cross entropy means that you're comparing these two classes, so being right or wrong, you're comparing the distributions with each other, and you represent it through this formula, which is right here. So in this formula, y is the class, so let's say being right. So P of y is the probability of being correct. So P of 1 minus y has to be the probability of being wrong. And we iterate this through the number of classes that we have. On the other hand, if we're trying to classify multiple objects, we'll use something called multi-class cross-entropy laws. And the equation looks something like this. O is the observation, so what the computer's thinking. C is the class. This right here is the likelihood that the observation is the class, and we represent this through y, being a binary indicator from values 0 to 1, telling us the confidence of that prediction. In both cases, we have to understand that getting answers wrong increases our lost value, and getting answers consistently right decreases our lost values really fast, which is why the log function is used. In both extremes, the model gets penalized to encourage a more sophisticated learning approach. When Facebook's AI research group created this model, they first resized the images to 800 pixels and trained it on 8 GPUs for 160,000 times. And if you're interested in the hyperparameters that they used for the model, here they are. And for me, after implementing this model and training it for 4 hours, this was my result. So yeah, I hope you enjoyed it, and thank you for watching.